So hopefully everyone had a good weekend. So today we're going to take up participation number 4, which I believe was question number 9 on 878. And then we'll take up assignment 1C, and then we'll do a bit of review in preparation for the test. And then the test is still scheduled for, when do we decide? Next Thursday, the 14th. I think that's when we tentatively decided to, yeah. So I'll put that in writing just so it's clear for everyone. And yeah, the test will just be an online test. I'll just email it to everyone in the beginning of class and then just submit it on Dropbox within 2 hours. And I'll be available over email for that as well. Okay, so if there's no questions, let's start on the participation question. Okay, recording is good. Okay, so it was page 878, number 9. So hopefully it's not too long of a question because these can get pretty long. Number 9. Okay, so it was the integral of, so the square root of 1 minus x squared over x squared, and then you have a dx on top, of course. So first thing I would do is I would look up what form, what substitution you have to use for this particular form. And actually it even summarizes it on page 878. So it looks like this one is in the form of square root of a squared minus x squared. So square root of a squared minus x squared. And it says to use the substitution x equals a sine theta. So in this case, if you compare this to the integral, you'll see that the a squared part corresponds with 1. So in this case, a is just 1. So for our substitution, at least it's a fairly simple substitution. It's just x equals sine theta, because there's no point in writing the 1. Okay, next step is start collecting everything you can. So you need a square root of 1 minus x squared in terms of this substitution. You need a dx, and then you need an x squared. So let's start with the most complicated part. Let's do the square root of 1 minus x squared, and let's substitute in sine theta for x. So square root of 1 minus sine theta squared. And it's at this point that you do the substitution that it recommends on the table on page 876. So the substitution is that we can replace 1 minus sine squared theta with just cos squared theta. So square root of cos squared theta. And then here, luckily, your square root and your square cancel out, which is usually the case. And then you just get a cos for that particular part. So for the whole square root part, it just ends up being cos theta. What else do we need? Dx is pretty easy to find. So x is sine theta, so dx derivative of sine is cos, so that would be cos theta. And then for the x squared part, we'll just put that in when we do the actual expression. That'll just be sine squared. So let's put everything in. So integral of, so here's just the original integral. So 1 minus x squared over x squared dx. And then you just substitute in everything that you've collected and just make sure that everything's accounted for. So make sure you take care of the square root, the bottom part, and the dx part. So this should be integral of, top should be cos theta. Dx should also be cos theta. And the bottom, x squared, should be sine squared. Sine squared theta. Okay, and for the top, I'm just going to write cos squared since we got a cos times cos right there. Cos squared theta over sine squared theta. Okay, so what to do at this point? I think what I would do, actually, I'm not sure at this point. So cos over sine, first of all, sine over cos is tan, so cos over sine is cotangent. So it looks like this is going to be the same thing as cotangent squared. So hopefully we have something in our chart for figuring out the square root, the integral of that. So I think that's probably the route to go here. Let me just double check my answer. darn it, I don't have it in front of me, so we'll have to just keep going and we'll see if it works. Okay, so yeah, you could take the square and you could just kind of surround the entire expression with it like this. So integral of, let's just do cos theta over sine theta squared. You're allowed to do that when you have a thing squared over another thing squared. And then cos over sine should be cotangent. So integral of cotangent squared. So let's see, hopefully we have a formula for that. Let's check the formula sheet. Formula sheet, chapter 28. So cotangent squared. Cotangent, I don't see cotangent squared. Darn, this is a tough one. Where is the integral of? I have cosecant squared, but I don't have cotangent squared. How embarrassing. Okay, I'm gonna just double check what answer I have for this. Just hold on, because I previously did it. So this is section, what section is this? 28.8, number 9. Let me just quickly find this, just to make sure we're going down the right track. And I have a million answers. Where are they? Everyone just bear with me. Okay, not that one. Not that one. Oh, here we are. Number 9. Okay. So yeah, so far it's completely right. So that's good. Okay, so at this point we use another common trig substitution. Since we can't find, since we can't integrate this directly, let's use probably one that's listed in the chart as well. Let's see. Oh, no, not listed in the chart. What is this? Why is there a battery over here? Okay. So for this one, let's look up our formula sheet just for trig identities. Which is listed in the chapter 28 resources. Let's just look that up, trigonometric identities, and we got, where is it? 1 plus cotangent theta equals cosecant theta. Okay, so if you rearrange that a little bit, you'll get cotangent squared theta equals cosecant squared theta minus 1. So that's just a common identity. Again, it's listed, it's called trigonometric identities. It's listed in the resources. So let's substitute that in because yeah, I don't know what the antiderivative of cotangent is, but for cosecant, that's definitely listed. So let's do that. Integral cosecant squared theta minus 1. I'll just put it around brackets for now and just put the d theta right there. And then the obvious thing at this point is to separate it into 2 integrals. And then one of them will be cosecant squared, and the other one will just be d theta, basically. So let's separate them. Integral of cosecant squared theta minus integral of, you could put 1 d theta. I'm just going to put d theta because there's no point in writing the 1. Okay, we're running out of room, but so far so good. And now let's look up what is the antiderivative of cosecant. It is, or cosecant squared, rather. It is minus cotangent. Okay, let me write this just where I have room right here. So this should be minus cotangent theta. And then for this part right here, of course, the integral and the d part just cancel out, and you're just going to have minus theta. And then you have your plus your constant. Okay, so that one was, the only tough part there was just using one additional identity. So there was, yeah, I got a bit stuck for a few seconds on that one. And then, of course, at the end, we run into our typical problem. The problem is that we had algebraic expression originally, and now we have something entirely in terms of trig without even having the original x variable. So we have to use our special triangle and convert this back into an algebraic expression. So I need some room for our special triangle. I guess we don't need much except for the answer and the original substitution. I think that's pretty much all we need to save for this. So I'm going to erase everything else. Yeah, let's get rid of this. Yeah, all we need is x equals sine theta in order to construct our special triangle. We don't really need, so we don't need this, don't need this, don't need this, don't need this anymore. And yeah, let's see, okay. So let's construct our special triangle. And this is the part that I think everyone mostly gets stuck on. You just have to remember to go back to your original substitution, which is right here, and construct a triangle based on that. So for sine theta, it's equal to x in this case. For the sake of clarity, I'm going to put, for clarity and consistency, I'm going to put it as x over 1, just because sine is always SOHCAHTOA, opposite over hypotenuse. So you want to write this in the form of a thing over another thing, just so you know exactly what everything corresponds with. And speaking of SOHCAHTOA, let's write that as well. SOHCAHTOA. Okay, so if you look at sine, it's opposite over hypotenuse. So in this case, x is opposite and 1 is hypotenuse. And now let's construct our fancy triangle. So we got this, we got a 90-degree angle right here. Let's pick theta right here. It doesn't really matter where you pick theta. You always have two choices. So this is the hypotenuse. This is adjacent, or sorry, I made a mistake. Let's erase this. That's not the hypotenuse, that's the opposite. Hypotenuse is always the across from the 90-degree angle. So that's the hypotenuse, adjacent and opposite. Okay, and this corresponds with, so x is opposite. So this is x, and this part gets a bit messy. So just try your best. Hypotenuse is 1. And it looks like we're going to need the adjacent side. Unless cotangent, so yes, yeah, cotangent involves, because tan involves opposite and adjacent, so cotangent will involve opposite and adjacent. So we do need to construct the entire triangle. Okay, so what do we use for this? We use a very old theorem, the Pythagorean theorem. So let's do that. So that is a squared plus b squared equals c squared. So let's label these appropriately on the triangle as well. So this, let's label this A, B, and C. So again, it gets really messy. There's pretty much 3 labels per side, which is really unfortunate, but there's not really a better way to do it. And then you just substitute everything in to the Pythagorean theorem where it belongs. So as you can see, C is corresponding with 1, B is corresponding with x, and then A will be what you're solving for, which in this case happens to be the adjacent side. So let's put all those in there. Okay, so A is just A, plus B squared is going to be x squared. And then if you look at C, that is 1, so that's going to be 1 squared, which is just 1. So I'm just going to put 1. Okay, and now we rearrange this a little bit, take the plus x squared, move it over to the other side, change it to minus x squared. You always have to change the sign when you're rearranging algebraic expressions. So hopefully I can fit it right here. So a squared equals 1 minus x squared. Good, good. And then you can square root each side to get a by itself. And it usually ends up, usually ends up being present in the original integral. Like if you compare this to the original one, it's the same expression we have on top. And again, for whatever reason, that always seems to be the case. So a is square root of 1 minus x squared. Okay, so let's write that on the appropriate side. Square root of 1 minus x squared. Okay, lots of work. Okay, so now let's plug this into cotangent, and for theta, we can just use, we'll deal with that in a second. We can use an inverse function for that. I think that's what we go, yeah, that's what we'll go with for that. So let's do the cotangent part first. Okay, so cotangent is, maybe I should just write, so tan is opposite over adjacent, so cotangent will be adjacent over opposite. So this should be minus, for now, I'll just write adjacent over opposite. Minus theta plus c, and now I'll plug the actual stuff in. So adjacent is square root of 1 minus x squared. Opposite is x. Good, good. Oh, and then there's a minus sign that just remains there. And then you have minus theta. So how do we find theta in terms of x? For that, we don't technically need to use the special triangle. All we do is we just look at the statement sine theta equals x, and we want to get theta by itself. So in this case, we do what we did in a couple of other examples. Again, you don't need the special triangle for this particular part. You just need to apply the sine inverse function to each side. And then by definition, you'll get theta by itself because that'll cancel out sine. So basically, it's just like sine inverse to this side and sine inverse on this side as well. I don't have a lot of room to write it. And then this will cancel, and you get theta equals sine inverse x. So you basically just apply a sine inverse to each side. You're allowed to do that as long as you do it for each side. So that should be minus theta, so that's minus sine inverse x plus your constant. Oh, geez, that was okay. That was a lot of work. But the answer looks good, so that's good. And I don't see any way of really simplifying it or anything like that. Does anyone have any questions about any parts of this? Okay, so everyone seems good for that. So now we're going to take up assignment 1C. So hopefully everyone has submitted that at this point. If you haven't, please do so in the next few minutes. Okay, I guess that's everything for this one. Let's get rid of this. And this is assignment 1C. Okay, so this was, for whatever reason, it was the exponential formula, the E formula, and then it was also integration by parts. I'm not sure why it was such a weird combination of topics, but whatever. So first one looks like one that is not too bad. It is just x to the 3, and then e to the minus x to the 4 dx. And just to recall, let's write the actual generic formula for this section. So it was integral of e to the u du equals e to the u plus c. So that's the formula for this. Okay, so for this one, u is going to be whatever the e is raised to. So let's check to make sure this is in the right form. It's almost in the right form. I can see that we're going to have to do like some manipulation with some constants. But other than that, it looks like it's almost already good to go. So u is minus x to the 4. So du is going to be, so take the derivative of u, so you get minus 4x to the 3 dx, because the exponent always drops down and then you subtract 1 from the exponent. Okay, so that's nearly the same as what we have in our original integral. The only thing we need to put in here is a minus 4, and then we'll be perfectly good to go. So as per usual, we'll insert a minus 4 in the integral, and then we'll offset it with a minus 1 over 4 outside the integral. And I'm also going to group everything together just for the sake of presentation. So let's do integral. I'm going to put this first, and then I'm going to put bracket, and then I'll put minus 4x to the 3 dx. I just like having it all to the right side of e to the u, because that's what they use for the standard formatting regardless. And then, so we just put a minus 4 in there. So let's offset this with a minus 1 over 4. Good, good. And now we can just directly integrate it. So the answer will just be, so the minus 1 over 4 will sit there, and then we'll just have e to the u. So that's going to be e to the minus x to the 4 plus your constant. And let's see, hopefully that's correct. Yep, good, good, good. So that one, yeah, that one definitely wasn't too bad. The next one looks slightly more complicated, although actually it ends up not being too bad if you just do one particular maneuver at the beginning of the question. So let's look at that one. And hopefully I'm not erasing these too quickly, but again, these are always available in the recording. Okay, let's do the next one. So this one is, let's see, integral of 8e to the 8e to the 8 sine 5x. Geez, that's kind of inconvenient. Oh well, 8 sine 5x over secant to the 5, or secant 5x. And then we got dx right here. Okay, so in this case, of course, u is going to be 8 sine 5x. So let's just write that. Let's just write that on the left. U equals 8 sine 5x. So here we have a bit of a problem because we need e to the u with du sitting next to it, but all we have is a secant 5x on the bottom, which is definitely not a good thing. Sorry. So what I would do is I would take the secant 5x and move it up to the top and replace it with its reciprocal function, which is cos. And then you're almost good to go because the derivative sign is cos, and all you have to contend with is just some of these numbers that they've inserted into this integral. Let's see, how should we do this? For now, I'm going to take the 8 and move it outside the integral. So 8 integral, and then for the e, I'll just keep that the same. And then I'll take the secant, move that up, and change it to cos. So that'll be cos 5x dx. Okay, so that looks a lot better than what it did a couple seconds ago. And now let's just take the derivative of u and let's see what we get. And if I make any mistakes or if I forget about any constants, please let me know. Okay, so du should be, so the 8 will just sit there. Derivative of sine is cos, so cos 5x. But then since there's a 5x in there, you have to take the derivative of the inside function. So a 5 is going to pop out of that cos. And that happens every time you have, every time you take the derivative of a trig function that has like a number next to the x. So a 5 is going to jump out. So let's put this together, I guess. 8 times 5 is 40. So let's just write this as 40 cos 5x. Okay, so that's not exactly what we have in our integral. So we need a 40 cos 5x. And this one is kind of further complicated by the fact that there's already an 8 there. So there is multiple ways that you can deal with this. But I think we'll stay consistent with what we always do. So let's just keep it simple. Let's just put a 40 in there, and then we'll divide by 40 on the outside. And the 8, again, can just sit there and chill. So let's do that. Okay, so for now, I'll just put 8 integral e to the 8 sine 5x. And then let's put 40 cos 5x dx. And then since I just put 40 in there, let's offset it. Let's put a 40 on the bottom below the 8. Good. Okay, and now 8 over 40 is, I guess that's just 1 over 5, right? Is it 1 over 5? Again, my arithmetic is always extremely bad. Yeah, that's just 1 over 5. So yeah, let's just reduce that to 1 over 5 at this point. And then for the rest of it, it looks like we can just directly do the answer. So it's going to be e to the u plus c. And then of course, it'll be 1 over 5 e to the, and u is 8 sine 5x plus c. So good. So that's correct as well. Good. Yeah, in this case, you could have done it a little bit differently. You could have kept the 8 in the integral and used it to kind of get that 40 cos. But I like just doing it the same every time, just inserting the original number, offsetting it, and then just simplifying wherever you can. Okay, what else do we have? I think that's it for the exponential part of the assignment. And then we have the, oh, there's a bonus question. Oh, this is a fun bonus question. I remember this one, yeah. Let's do the bonus question. Okay, getting rid of this. Yeah, this bonus question is one of those that looks super complicated, but you just actually have to use some basic algebra to rearrange this, and then you're pretty much good to go. So it's e to the x plus e to the minus x, and all of that is squared, and then dx. So at this point, you can't really do anything. You can't directly use the exponential formula because you don't have it in the correct form. There is no e to the u du sitting next to it because you got e to the x, you got e to the minus x, and further complicated is the fact that that entire expression is squared. So what I would do is I would just expand out the brackets and see what you get. So in this case, you have e, so let me illustrate that on the side. So you have e to the x plus e to the minus x squared. So any expression squared is just that expression times itself. So let's just do that. So it'll be e to the x plus e to the minus x times e to the x plus e to the minus x. And then we're just going to expand out the brackets and see what you get. And then at least you have like a bunch of e's kind of with plus signs between them, or maybe some minus signs depending on what the question is. And that's a lot easier to deal with because in this case, we're pretty much inhibited by the fact that it's the entire expression squared and we can't really do anything. You can't even use the general power formula because even that isn't in the correct form. So expand out the brackets. So this one goes to this one. So that'll be e to the x times e to the x. I'll just write out everything in its basic forms and then I'll simplify. So e to the x times e to the x. Next one will be this one, e to the x times e to the minus x. So plus e to the x times e to the minus x. And then next one will be this one. So that'll actually be the same expression. So I'll just write that again, plus e to the x times e to the minus x. And then last one will be e to the minus x times e to the minus x. Okay, so this looks pretty ugly, not looking too good, but have faith. So e to the x times e to the x is you just add the two x's, so that'll be e to the 2x. The other ones actually simplify really nicely. So if you have e to the x plus minus, so let me just here, I'll just write this off to the side. E to the x times e to the minus x will be e to the x plus minus x, which is, of course, the x and the minus x cancel out and you get e to the 0. So what the heck is e to the 0? Well, anything to the 0 is just equal to 1. That's just like a general exponent rule. It doesn't even matter what the original base number is. It's just it automatically regresses to 1 if you raise something to 0. That's just so that they can maintain like consistent exponent laws. So this one will be equal to 1. This one will be equal to 1. So 1 plus 1 is 2. So let's just put 2 right there. And then this one right here, you add your exponents. So minus x plus minus x is minus 2x. So plus e to the minus 2x. And okay, I think I'll rearrange this just for no reason really, but I just like having the constant on the right side. So it's e to the 2x plus e to the minus 2x plus 2. So that's what we get so far. And now this is a lot easier to integrate because each of these individually are very easy to integrate. So let's integrate these. Okay, so integral of e to the 2x plus e to the minus 2x plus 2. And then let's put brackets and then we got dx. And then of course you can split this into individual integrals and do them each by themselves. Let's see, or you could just kind of do it directly. It's up to you. Just for the sake of time, I'm just going to do each of these. I'll just bring each of these directly to the answer. So e to the 2x is just going to be itself. But because you have that 2x there, you do need to offset it a little bit with a 1/2. Because if you hypothetically took the derivative, the 2 would pop out and you would need to cancel it with something because there's no 2 in the original integral next to the e to the 2x. So I'm skipping kind of a little steps here, but again, just kind of to save time. Next one should be itself. And we're going to have to put a minus 1/2 out front to hypothetically cancel out the minus 2 that's there. And then the integral of 2 will just be, so that'll just be 2x. or yes, no, yes, yeah, 2x, yeah. 2x and then plus your constant. So that one wasn't too bad. You just have to know basically just to factor out, or sorry, expand out the brackets, and then each of them individually is fairly straightforward to solve. Okay, so that was the bonus one. Oh, someone has their hand raised. Go ahead.
Yeah, I kind of did a bunch of research on this one because I got confused at first.
Mhm.
I came out with that e to the x plus e to the negative x ends up being, hold on, I have it right here. It's actually the hyperbolic cosine function.
Yeah, I don't think that applies in this case because you specifically have e to the 2x and e to the minus 2x. I don't think you need to go
right off the bat though.
Right off the bat. Okay. I've never even looked up those functions, to be honest. Did you get the same answer, or what was your answer?
I ended up with 4/2 times 1/2 sine h2x plus x.
Oof. Yeah, I would stick with just using this method because I can't really confirm if that's correct or not. Yeah. I would. So yeah, in this case, I think it's probably. Darn, that's a tough one because, like I said, I haven't looked up those functions. They're not part of this course. So when I look at your assignment, I'll look at it, and if you do get the correct answer, then I'll give it to you.
Okay, sweet.
But overall, I think that this is the better method because, at least in this case, it's just basic algebra, and then it's just a direct application of the exponential formula.
Yeah, that's for sure a lot simpler, and I figured that I was a little bit off on a tangent, but
I'll check it out for sure.
okay,
No
sweet.
worries. Okay, so next one is oh no, it's the integration by parts, which is always a bit of a pain, but actually these ones look pretty, yeah, these ones look not bad. Yeah, these assignments used to be like 2 or 3 times as long, and then just every year I just cut them down. Let's see, let's get rid of this. Okay, so use integration by parts to evaluate the following integrals. Makes sense. This is ln 2x dx. Okay, so this is virtually the same as one that we did in class. The only difference is that it's a ln 2x rather than a ln x. Okay, so what should we pick in this case? So we have to pick a u. Let's do this over here. So you have to pick a u, and then we have to get our du, of course. And then we have to pick a dv, and then we have to regress and figure out the original v. And then let's write the original formula as well, which is, let me check that out on the formula sheet. Original formula is integral of u dv equals u times v minus integral of v du. Okay, so lots of stuff going on. So for this one, for a choice of u and v, there's really only one choice for u, which is to pick ln of 2x, because I don't know how to take the antiderivative of ln off the top of my head. I think that question in itself is pretty much this question. So yeah, that would be, so definitely pick u as ln of 2x. So let's do that. Ln 2x, and then let's take the derivative of ln of 2x. So in this case, the 2x would drop down to the bottom, and on top you would have the derivative of 2x, which is just 2 dx. So let's do that. So let's see. So at the bottom is just 2x. At the top is 2 dx, because whatever is inside the ln always drops down, and then on the top is always the derivative of that. So in this case, it's actually very nice that you happen to have a 2 on the top and the bottom, and they just cancel each other out. So that's nice. So goodbye, and it'll just be dx over x. So that's very good. And then for dv, you only have one choice. You just have dx left over, which is also very nice. So dx will go right here. And then if you regress and take the antiderivative of that, you'll get x. So far, so good. Okay. So we have our u, our du, our dv, and our v. So now let's just plug everything into this. So u is ln 2x. dv is this one right here, dx. Actually, wait, does that, oh, sorry, that should, yeah, that doesn't make sense. It should be v. V is just x. Okay, yeah, that, because that right away, that seems to not make sense. So at least I noticed the mistake. Minus integral of v, which is x, and then du, which is this one right here. So dx over x. Okay, so this one is working out pretty nicely, actually. Okay, so for the ln 2x times x, again, I'm just going to take the x and move it to the left side because I don't want the reader to think that it's part of the actual inside of the ln, because it's not. So x ln 2x. So that's perfectly fine. That'll just sit there and chill. And then minus, okay, so for this integral, this is a nice one actually. So the x's cancel out and you just get minus the integral of dx. And you could literally just scratch out the integral, scratch out the d, and you just get minus x plus c, because an integral and a derivative are opposing forces. Is that it for that one? Okay, so that one wasn't too crazy. And in this case, if you wanted to simplify your answer a little bit, you could just take the x and factor it out. It doesn't really make that much of a difference. So you could do x bracket ln 2x minus 1 plus c. Either answer is fine. Factoring it in this case doesn't really simplify it all that much. So both are good. Does anyone have any questions about that one? Okay, so let's do, I guess there's just one more, unless there's another bonus one, but I don't think there is. Yeah, it looks like there's just one more. Okay, so and the next one is definitely a weird looking one. Let's just, hold on, let me find, here it is. Okay, let's get rid of this. So this one is integral of sine x, and then you have ln cos x, ln of cos x dx. Okay, so yeah, definitely a weird one, but in this case, you have very limited choices, because for you, you're definitely gonna have to pick the ln part, because again, we don't really know what the antiderivative of ln is. I'm sure it's in the back of the textbook, and we pretty much just figured it out in the previous question, but it's just way easier just to pick u as whatever is associated with ln. So let's do that. And actually, hold on, before we do that, let's just write out the generic formula. It is, this formula is so hard to remember, at least for me. I don't know why, because it's kind of an arbitrary formula. Integral of u dv equals uv minus integral of v du. Okay, so let's pick our u. So u, let's do ln of cos x, because we don't really have much of a choice in this case. And now let's take the derivative of that, which looks difficult, but you just follow the ln derivative formula, which is whatever is inside the ln drops down to the bottom. So let's do that. So that would just be cos x. And then on top is just the derivative of cos x, which is minus sine x, right? Yes, minus sine x. That actually gives you minus tan. I wonder if we should use that or not. I don't think so, because we should expect probably some cancellation later. So we'll just leave it like this. For the rest of it, for dv, you'll just have to choose, in this case, whatever is left over, which is sine x dx. And then you regress backwards and figure out the antiderivative of that. So antiderivative of sine is minus cos. So v equals minus cos x. Yeah, because derivative of sine is cos, derivative of cos is minus sine. So that, yeah, so that works. I always have to repeat that in my head because that's the only way I can remember it. Okay, so not too bad, as long as you kind of know the, your derivative formulas for ln and for your trig functions. And now let's plug everything in. So it should be uv minus integral of v du. U is ln cos x. I'm going to run out of room doing it this way. I'm going to do it on the bottom. Sorry. U is ln of cos x. Good. V is minus cos x. And I'm just going to put that on the left right here, minus cos x, because I'm going to do that eventually anyways. Again, that's just for clarification for the reader. And then we have minus integral of, okay, so V is minus cos x. Good, and then du is minus sine x over cos x. Minus sine x over cos x. And then we need a dx. Oh yeah, there should be a dx right here. Dx right here. Okay, so what should we do? There's a bunch of stuff we can cancel right off the bat. So there's two minus signs within the integral. So let's get rid of those. And then you could also cancel out the cos. So goodbye cos, goodbye cos, goodbye minus sign, goodbye minus sign. The minus sign outside the integral just remains there because there's no other minus signs left over to cancel that. Okay, and now we just have to take the integral of sine x, which is, well, we actually just did that a second ago. It's minus cos x. So this should be minus cos x ln of cos x minus bracket, and then that's going to be minus cos x. So in this case, again, you happen to have two minus signs. One was just originally there, and one is just part of the actual formula for the antiderivative of sine, plus c. Good, good. So in this case, there's just one last obvious step. Just cancel out the two minus signs. So the final answer should be minus cos x ln of cos x plus cos x plus c. Okay, not too bad. So again, you need some basic derivative stuff. You need to know how to take the derivative of ln. Obviously, you need the integration by parts formula, and then you just got to be careful with the cancellation and just do it very deliberately. Good, good. So that looks right. Yep, that's good. So let me just double check that this is all of the assignment. Yep. Okay, so that was the whole thing. I'll try to get the marks up for that at some point this week. Yeah. So if anyone has any questions about that, let me know. And for the solutions, I'll just refer people, of course, just to this recording. I'm not going to post a PDF because for this, all my PDFs are chopped up because they're all from it's like 3 different PDFs just for me to look up the solutions because this is all from previous stuff. Okay, good. But at least there's the recording for everyone. So I guess that's everything for the initial stuff. And then I figured what we'd do next is just a little bit of review in preparation for the test. So I don't really have much prepared, but there is a review section. I figured we would just improvise and see if we can figure these out. Let me just, I'm just gonna go, give me a second just to, actually, maybe it's a logical time just to take a bit of an early break. I think that makes sense. Yeah, let's do that. So everyone take a 10-minute break, and then we'll come back and we'll do a couple of review questions. So let's do a couple of review questions. We're not going to do anything too big at this point. Later on, I'll probably do a little more formal of a review. Okay, so this is page 892, and it just says chapter 8 review questions, or chapter 28 review questions rather. So page 892, and we'll just do a couple of these. First one is like so basic that it's almost not even worth doing, but we'll just start off with something not super complicated. And it looks like these are all just random, so you do have to kind of figure out which formula to use. Same thing with the test. It won't be specified what formula to use, so you do have to be familiar with which to use for which question. Although like it's pretty much like one question per formula that we've covered. So it's like not much of a mystery in that regard. Okay, so integral of e to the minus 8x dx. So just that. So this, of course, will just be an application of the exponential formula. Here's the formula right here. Integral of e to the u du equals e to the u plus c. So let's just set u as appropriate. Let's set it as minus 8x. Let's take the derivative and just make sure that it's in the correct form. We'll have to do a bit of an adjustment because, of course, there's a minus 8 there, and that's going to pop up. So u will be minus 8x, and du will be minus 8 dx. So it's almost in the correct form. We just need a minus 8 within the integral. And then, of course, we'll offset it by putting a minus 1/8 outside the integral. So let's do that over here. So integral of e to the minus 8x. And now let's do bracket, and let's put minus 8 dx right here. And let's put minus 1/8 right here. So remember, whenever you put constant into your integral, you always have to offset it. And now we can just directly use the formula. So that's going to be minus 1/8 e to the u plus c. So that'll be minus 1/8 e to the minus 8x plus your constant. And yeah, so that one, not much to say about that one. That's pretty much just a direct application of the e formula. But then there's another one, which is number 2, which is a really interesting one, which like took me a second to figure out. It's definitely a weird one, and it requires a trig identity that we don't use super often. So let's try number 2. We're still recording, good, okay. Okay, so this one is, and it's a weird looking one for sure. It's e to the cos 2x times sine x cos x dx. So right off the bat, when I looked at this, I was like, this is it's a bit troubling because of course, u is going to be cos 2x, and then you're going to take the derivative of that, and you're going to see if it's, what you have sitting next to your e to the u. But in this case, there's a problem because first of all, the other trig functions is just sine x and cos x. But the other cos raised to the e, or that e is raised to, has a 2x in it. So that kind of screws up like absolutely everything. But on the other hand, there is a trig identity, which can take a trig function that has a 2x in it and kind of get rid of the 2. That is the identity. Let's just write it down right now, because that's what kind of jumped out at me. Where is it? It's somewhere. Oh, right. It's the trig identities document. So it is, actually, let's hold off on that for 2 seconds. Let's first take the derivative of u, and then we'll see what identity we want. Let's just get our bearings. So of course, the overall formula we're going to use is same thing, just e to the u du equals e to the u plus c. Okay, so let's pick u as being cos 2x. And now du will be, so derivative of cos is minus sine, and then a 2 is going to pop out as well. So du equals minus sine 2x. And then the 2 pops out, and I'll put it right here. So that works so far. So yeah, derivative of cos is minus sine. Good, you got the minus 2, or you got the 2 popping out there as well. So that's good. Okay, so at this point, I would take note of the fact that we have a sine of 2x, which is still a major problem because none of the other trig functions have a 2x in them, and you can't just take a 2 out of sine. You have to use like a proper trig function. Whatever is like sitting inside of a function, you can't just remove it unless you have a specific rule that you're using. So let's just look at this identity that comes to mind. The identity is, it's called a double angle identity. It's listed on the, again, the trigonometric identities document. And it is sine of 2x equals 2 sine x cos x. So that is really, really awesome because that basically transforms du into exactly what we need. There's a sine x and a cos x, and that indeed is what is in the original integral. So let's just substitute that in right here before we even do anything. Let's just put that in and fully develop this. So the -2 will sit here. That's already there. And then sine of 2x, replace it with this identity. So you're going to get, you're going to happen to get 2 2's in here just because one was already there and one is right here in the identity. So 2 sine x cos x. And let's just simplify that and we'll just put -4 sine x cos x. So for this question, oh, and then we need a dx as well. I always forget that. So for this question, without this particular identity, which is not a super well-known identity, but at least it is on the sheet, I don't know if you'd be able to solve this without that identity. There might be other ways, but nothing comes to mind. So you definitely have to use that. Okay, so it's almost in the correct form because we got sine x cos x dx, but there is a -4. So we should put a -4 in the original integral, and then we'll offset it with a -1/4 out front. So integral of e to the cos 2x, and then bracket -4 sine x cos x dx. And then we'll put a -1/4 right here. So it looks kind of ugly, but it is in the correct form now. It's e to the u with the du sitting next to it. So you can just directly integrate. So you get -1/4 e to the u plus c. A lot of the times I just write e to the u initially, just so again, just kind of to stay organized, but you always have to, plug your original variable in there. So let's do that. So -1/4 e to the cos 2x plus c. So that one was a weird one, but it was at least it was interesting, and hopefully I got the correct final answer. Yes. Good. Okay, so not too bad. Ooh, the next one's also a really, really weird one, but it ends up being a fairly straightforward formula that you use. So let's do that one. So number 3 is integral of dx over x times ln of 2x squared. So yeah, this one's a weird one. So what jumps out to me is that we could probably use the general power formula, because I don't think we could use a ln formula here, because the ln 2x is raised to an exponent and it's at the bottom. So it's not really appropriate for the logarithmic formula, because that should be in the form du over u, which just, it doesn't look like that's what we have. But there is an exponent, and we do know actually from a couple minutes ago that the derivative of ln 2x is actually just dx over x, which we actually have in the expression. So all of the signs in this case, despite it looking weird, lead me to believe that we should use the general power formula, which was the first formula that we looked at, which let's just write down if I can remember it. It's u to the n du, or integral of u to the n du equals u to the n plus 1 over n plus 1 plus c. So it was that formula right there. So it doesn't look like that would work in this case, but if we rearrange it, I think we can get there. So I'm going to rearrange this a little bit. I'm going to take the ln 2x and I'm going to bring it up to the top, and then I'll change the exponent to a minus, because if you do something like that, you have to change the exponent. And then I think I'll write dx over x to the right of that, and I'll put brackets around that particular part, because that's going to be the du part. So it'll start to look a little more like we can use the general power formula. So this will be integral of ln of 2x to the -2. So that's the same thing as before. Again, you have to switch the sign in front of the exponent if you want to switch something from the top to the bottom, or vice versa. And then the rest of it, let's put as dx over x. So now it looks like it actually is in the correct form. You do have a u to the n, and then you have a du sitting next to it. Let's confirm that that's the case. Let's set u equal to whatever's in the exponent brackets. So u is ln of 2x. And now let's take du, and let's see if we do indeed have du sitting next to our expression. So du is going to be, so for taking the derivative of ln, whatever is in ln drops down to the bottom, and then you take the derivative on top. So 2 dx will be on top. Again, we just did this kind of a few minutes ago. And then the 2's happen to cancel out, which is nice. And then you get dx over x. And surprise, surprise, that's exactly what we have sitting next to our ln of 2x to the minus 2. So if you compare this to this, it actually is in the correct form for a u to the n du maneuver that you can use. So why don't we just directly integrate this now? Because everything is good to go. And yeah, so maybe should we use u or should we just use, let's just use our original stuff. So ln of 2x, so add 1 to the exponent and divide by that number. So that'll be minus 1 divided by minus 1 plus c. And then, of course, you can kind of clean this up a little bit. Let's see. So the minus 1, there's no point in having a minus 1 on the bottom. So you could just get rid of the 1 and just put the minus on top. So let's just do that for now, and then I'll see what else we can do. So minus ln of 2x to the minus 1 plus c. So you could keep it like this. I'd be fine with that. Another thing you could do is you could, drop the ln 2x down to the bottom and change the minus 1 to a plus 1. And in that case, there's no point in writing an exponent of plus 1. So basically, you could just drop the expression down to the bottom in this case. The minus would stay at the top because there's nothing, the minus is its own thing. So at the top, you would just end up with a minus sign, which is just minus 1. So you would get minus 1 over ln of 2x plus c. Yeah, because in this case, the only thing you can drop down is just what's applied to the minus 1. Everything else just stays at the top. So that's why the minus sign hangs out at the top. And you can't just have a minus sign at the top. You got to have it's minus 1. So minus 1 over ln of 2x. So yeah, a lot of these are, it's kind of tough to figure out which formula to use, and you might have to use some manipulation. On the test, I usually don't try to be very tricky. On the test, it's usually just testing to see if you can just solve a standard problem using whichever formula. Usually they won't be this obscure and this tricky. Let's do an easier one. Let's do one that's not as much work. We got some inverse sign or inverse functions, it looks like, or inverse trig integration questions, I should say. Let's do one of those. Let's do number 7. So this is integral of 2 dx over 25 plus 49x squared. 25 plus 49x squared. Okay, so this is going to be one of our inverse trig functions. Yeah, it looks like it's in the perfect form for that because it's on the bottom, you have a thing squared plus another thing squared, which I'll kind of reorganize the bottom in a second. Oh no, my laptop's dying. Oh well. Okay, so let's just look up the inverse functions because there was 2 of them. There was the tan one and there was the sine one. Let's look them up because I don't remember them. And let's see which one we will use. So they were, what section was this? 28.6. And this is, it looks like we're going to be using the tan inverse function. So let's write that formula down. It is integral of du over a squared plus u squared equals 1 over a tan inverse u over a plus c. So that looks like it's going to work perfectly. There's nothing to mess this up. If there was like an x on the top or an x squared on the top, it would completely eliminate this method of solving, and you'd probably have to use trig substitution, which would really suck, or something more complicated. Yeah, so in this case, it looks like it's perfectly good to go. So let's just establish everything. Or actually, for the bottom, let's first rewrite a couple of things. And then we got that 2 there. I don't know why they bothered putting that 2 there. I'm just going to put it outside the integral and we'll forget about it for now. 2, okay, so integral dx. And now let's try to write the bottom so that it's in a comparable form to the generic formula that I just wrote. So 25 is 5 squared, because 5 times 5 is 25. So that part's not too bad. So 5 squared for that, good. Plus, now in this case, you have 49, which is 7 squared, and you have x squared. So you have a number and a variable squared. So what I would do is I would take 7 and I would take x and I would put them both around brackets around both of them. And I would put the square around the brackets. And then it's technically applied to both of them. So if you imagine the square attaching to the 7, you got your 49, so that's covered. And if it attaches to the x, you got your x squared, and that's covered as well. So it is the same thing, but now finally it's in the form of a squared plus u squared, where u happens to be 7x. So let's just write down exactly what we got. So a, in this case, 5 squared is a squared, so a is just 5. And then u will be 7x. So let's just write those down just to be safe. And now it looks like we can just use the formula. So let's do that. So the 2 will sit here. And now for the formula, 1 over a is 1 over 5 tan inverse, and then u is 7x over a, which is 5 plus c. So then, of course, you could simplify this like a tiny, tiny bit. You can just, you got 2 times 1 over 5. So I would just write that as 2 over 5. I don't see any other simplifications that we can do, though. So 2 over 5 tan inverse 7x over 5 plus c. Okay, so not too bad. Usually the inverse ones aren't bad as long as you know kind of like how to do a couple of tricks with like squares and square roots and stuff like that. Let's see if there's anything else that is interesting in this review section. Here it is. Okay. Just give me a second to check some of these. So we just did number 7. So there's another one that's just a trig inverse one. There's another one that looks way too long. Let's do.
For that last one sec.
Sure.
Do you not have to prove that du, like the u and the du coincide, like the derivative?
Oh, right. Yes, you're right. Sorry about that. Yeah, because you need a du on top right here. You're exactly right. Yes. Sorry about that.
We don't have the correct solution here then, because that would be 7 dx. You have to put a 7 in the numerator, so it would be 2 over 7.
Absolutely, you're correct. Apologies about that. I'm glad that someone noticed that. So let's just start off. Let's just erase this part, and let's just kind of start fresh a little bit. That's my mistake. I forgot about yeah, you need the du on top. You always got to check that. So the only difference is that there's probably going to be a 7 in our answer that wasn't previously there. So let's do du. So du is 7 dx. So absolutely, we do need a 7 dx on top, which we don't have at this point. So what you'd have to do is do an adjustment. So put a 7 right there, and then put a 7 on the bottom to adjust for that. And then you'd be able to do the answer from there. So you would get 2 over 7, and then you can just directly use our formula. So the formula was 1 over a, so 1 over 5 tan inverse, and then u over a is 7x over 5 plus C. So yes, very good point, because if you look in the original generic formula, you got du right there, and we did not originally have du on top. We were missing that 7. And then you could simplify it a little bit on top. For this part, you can just get a 2. And then on the bottom, 7 times 5 is 35. So 2 over 35, tan inverse 7x over 5 plus c. Very good. Thank you for the correction. Okay, let's just do one more. And this one is not too bad. Okay, so clear this one. So this one is number 11. And it is a definite integral, so it has upper and lower bounds, which are always kind of a pain, but it happens. So you got upper bound of 2, lower bound of 0. You got x dx over 4 plus x squared. So I think in this case, I would initially be tempted to try maybe an inverse trig function, but that's not going to work because you have an x dx on top. If you just had a dx on top, it would work. But because of the way the inverse trig functions are set up, it wouldn't quite work. In this case, it looks like we have it in the form of a logarithmic function. So let's just look at the generic formula for the logarithmic formula. So that was du over u equals ln of absolute value of u plus c. It looks like that's what we have here. It looks like we have a function on the bottom with the derivative of that function on the top. And this was like the second or third formula we had. It was a while back. So let's go through this, and we'll try to be a bit more careful than the previous question. So let's set u as the bottom function. So 4 plus x squared. And then we'll figure out what du is. So the 4 disappears, and then the x squared will be 2x dx. 2x dx. So good, that is what we have on top. So it is in the correct form, basically. We just need that 2 on top. So maybe we should just add it without bothering to rewrite the integral, just to save a bit of time. So I'm going to put a 2 up here, like this, and then I'm going to offset it with a 1 over 2 right there. Okay, so I guess we can just directly apply the formula now. So this will be, and for now, I'm just gonna write it without the upper and lower bounds, and then I'll include those in a second. So 1 over 2 ln of absolute value of u, which is absolute value of 4 plus x squared. And then since it's a definite integral, you don't have to bother to include a constant. And now let's put these lines up, this one and this one. And this is just notation to let you know that now you have to plug in the upper and lower bounds. So what's the best way to do this? I think we should keep the 1 over 2 outside of everything, so we don't have to carry it through the entire expression. So let's just put the 1 over 2 right here. Maybe we'll put some square brackets. And now we have to plug in 2 into the ln expression, and then put minus, and then plug in 0 into the ln expression. So ln of, I'm not going to bother putting the absolute value anymore because it's all positive, so it doesn't really matter. Okay, so ln of 4 plus, and the upper bound is 2, so 4 plus 2 squared. And then minus, and then you do the same thing, except you put in the lower bound. So that's ln of bracket 4 plus 0, so just ln of 4. Okay, so far so good, and now let's just keep going and see what final answer we get. So 1 over 2 square bracket ln of, so 2 squared is 4, so 4 plus 4 is 8. So ln of 8 minus ln of 4. So one thing that's nice here is we can use a ln formula to combine these. Because you might recall, I'll just write this at the top, there's the ln formula that ln of x minus ln of y could be combined into 1 ln as long as you change it to division. So we can do that. Let's do that. So this is 1/2 square bracket ln of 8/4. So 8/4, of course, is just 2. So this is 1/2 ln of 2. That's pretty cool. You could also do another thing that's kind of neat. There's another ln rule that says, let me try to remember this, that ln of a to the n is equal to n times ln of a. It's actually kind of a cool rule where if you have ln of something raised to an exponent, you could actually just remove the exponent and just put it as a number outside the ln. So that's another kind of cool ln rule. So in this case, we have a number sitting outside of ln. So if we wanted to, we could just kind of take it and actually just attach it as an exponent to the 2. Is that a worthwhile simplification? I think so, because at least then you just have ln of whatever number. So let's do that. So it's kind of the reverse of this little formula right here. Like we're starting with this part and then we're transferring it, kind of making it like that. So this could be written as ln of 2 to the 1/2. And of course, anything raised to the 1/2, it's the same as the square root. So finally, we get ln of square root 2. So that's simplified really, really, really nicely. So I would just accept ln of square root 2 as an answer, because it's likely a decimal number that goes on most likely forever. So if you just wrote ln of square root 2, that's perfectly fine. It's kind of the equivalent of writing pi as an answer. But if you wanted to get the actual full answer, then let's, just for the sake of doing that, let's see what we would get. So ln of bracket square root 2 and bracket equals, and you get, I'll just write out all the decimals. You get 0.34657,359. So either answer is fine. The ln of square root 2 is a little bit better because it represents the entire number. This one's not quite as good because you hypothetically cut off infinitely many decimal points. So if you are going to write it as a standard number, just go to a bunch of decimal points. Usually 6 is pretty standard. In this case, I just wrote them all down. Okay, so that was a neat one. The actual formula in this case wasn't too bad. Okay, I think that's good for today. We're almost done. We're almost out of time regardless. So let's stop sharing. So does anyone have any questions? So I think on Thursday, maybe we'll move on to something new, or maybe we'll do a more expansive review of the chapter. But again, just remember, test is tentatively scheduled for the 14th. Okay, so if there's no questions, I guess that's everything. So everyone, thank you for coming. Have a good day, and I will see you on Thursday. Bye-bye.